Okay, welcome everybody. Hopefully those of you who can hear me, welcome. Hopefully those of you online can hear me as well. If you can, go ahead and send me a chat. Do you want to mute that actually? Excellent. You got it? Okay, perfect. All right. Yeah, again, thanks for joining us, everyone. You are attending the First Friday Astronomy event hosted by Boise State Physics. Those of you online, you've dialed into the First Friday Astronomy. My name is Brian Jackson. I'm a physics professor here at Boise State, teach astronomy and physics. You are attending a monthly event. This happens on the first Friday of every month. I think most of you probably know this already, but this happens on the first Friday of every month, 7:30. We bring a speaker in. They talk some kind of space science. So we've had, of course, astronomers, planetary scientists, but we've also brought in science journalists, space policy people. We've got a lot of really fun talks lined up for you this summer. This is the first of our summer session. So these events take place all throughout the year, all 12 months. So even if the school is shut down over the summer, we still have these events. So don't hesitate to come out. Our next event is going to be on June 3rd, where we're going to have Dr. Andres Salcedo, who studies cosmology and weighs galaxies using gravitational lensing. That should be a really fascinating talk. We are also going to partner on June 3rd with the Boise Astronomical Society to host their world famous So You Got a Telescope event, where folks bring in their telescopes that they either got gifted or they found in their closet or they're just pulling out of the garage for the first time in a long time. Bring them down to campus and we teach you how to use them. So come on down to campus June 3rd. You'll have the treat of the Boise Astronomical Society teaching you how to use your telescope. And then after that, we'll have Dr. Andres Salcedo give his lecture at 7:30. So more information about that online soon. Okay, and we are very fortunate tonight to have just a fantastic speaker. I think you're going to really enjoy this talk. Dr. Christie Swann is a planetary aeolian scientist. She got her degree, a bachelor's degree and a master's degree from Eastern Carolina University, and then a PhD from Texas A&M. She studies coastal science for the Naval Research Lab and studies the processes that drive sand motion on the Earth, but also on Mars and other planets. She is an award-winning scientific author and just a fantastic speaker, really great person. I think you're going to enjoy this talk a lot. And with that, I'm going to turn it over to Dr. Christie Swann. Let's give her a welcome.
Thank you. Is the screen share on? Or can you do it? Yeah, clicking, nothing's happening. I may have broken it. Very good at breaking things. I was taught in my PhD that you haven't really done field work until you've blown something up. So I've been really good at messing with technology and finding the limits.
Wow, I see you made that already.
I blew up a sound card. I was trying to sample some signals for these piezoelectric sensors I was building for some Mars low pressure wind tunnel work. And yeah, I blew it up, caught some fire in the lab and no sprinklers went off. So that was good. Yeah.
Okay, I'm gonna turn the lights up. She's got some very neat videos you're gonna need dark for.
Yeah, so thank you so much for having me. I am really excited to be here. I currently work for the Naval Research Laboratory doing coastal science for naval operations. But I also, when I got that job, I was like, hey guys, I still want to do planetary science. So I also do some work for NASA and I study windblown sand on Mars. So wind and sand are like my favorite things. And that's what I've become obsessed with and has become my life's journey. So Brian asked me to kind of tell my origin story because it's very different from, I think, most traditional planetary scientists. So I'm going to tell you a little bit about my life. It'll take about 5 minutes, and then we're going to get into the presentation. So I grew up in rural North Carolina, and I was a dancer. So I danced from age 4 to like 2021. And I went to college for dance when I was, back in North Carolina. I was really good. I had performances. And so I was like, okay, I want to do this for my life. I'm going to be a dancer. And I went to college for dance, got into the school I wanted to get into. And I was working under Joe Corot, who was a principal dancer for the American Ballet Theater from age 19 to 25, which is like the pinnacle in America that you can get to. So it's the most graceful 55-year-old man I've ever seen. And we were dancing from 9 to 2, Monday through Thursday, almost just all the time. And I was realizing during that time of my life that I really, dance had become less of like this stress reliever and more of a job. And I just started not liking it as much. And I started not getting as, the excitement out of it. So at the end of my 3rd semester, Joe Corot pulled me aside. He was like, Christie, can you please stay after class? And I was like, oh my goodness, Joe Corot's asking me to stay. I'm so excited. But he told me that I was going to have to change majors. He said, you're not progressing like the rest of the group, and you're not going to make it in the dancing world. And this is literally all I had done or really been known for. It was my complete identity. So complete failure. Like I failed really hard. But I'm so incredibly thankful for that failure. And the reason is because it is why I'm doing what I'm doing now, which I completely fell into. So at the end of my 3rd semester, I had to sign up for classes for the 4th semester. And I went to an undecided majors advisor, and they asked me, well, what do you want to do? An engineer, a teacher? Nothing was exciting me. And finally, they asked me, well, what's your favorite thing to do? Like nothing to do with a career. And I said, hang out on the beach with my friends. And they told me I could study the beach. And I was like, what are you talking about? I'm a dancer in this, just no idea how that would work. And I signed up for some classes, and I was incredibly insecure because I was a dancer and now the science world. And so I worked really hard because I was always training as a dancer, but now I was in these science classes. And then one day a professor comes in during my 4th or 5th semester, and in college, this is like 1st or 2nd semester in the earth science world. And they were like, hey, we're going to the field. Does anyone want to come? We need field help. And I was like, oh, a free trip to the beach. They're going to pay for my food. I get to suck up to the teacher, which I need to do because I'm definitely not going to make the grades that everyone else is making. So yes, I will go. And I found myself hammering in these things called anemometers, which I now help build and design the latest tech in doing that. And we're trying to put some on Mars. But I was hammering in this thing called an anemometer into the side of a dune. And there was this anemometer and a cable going back to this weird looking box that had digital things on it. And that was going back to some laptop. And I'm looking at the laptop screen. And as the wind gust came, it blew really hard. I saw this voltage spike, and I had this major epiphany. And I realized, oh, this is how science is done. And from that moment, which I can remember like it was yesterday, I have been addicted to windblown sand. And now I build instrumentation, and I get to work with amazing scientists like Brian and try to design landers to measure windblown sand on other planets. How cool is that? So success from absolute failure. So if you don't have a plan B, that's okay. You're probably going to stumble into it and it's going to work out. So just keep going. Okay, so that's my origin story. So what I'm going to ask you to do today or this evening, is to help us design a lander. Whenever I talk about this, when I go through these presentations or these slides, think about how we can measure wind and sand on another planet. And the reason I'm asking is because we're really trying to do this, and it's really hard. And we can only do this when we have a communal effort from multiple people and multiple different backgrounds to be able to actually do something of this magnitude. We're talking like the most expensive field experiment ever. So we need all the big brains that we can to do it. So as I go through this, imagine what you would deploy if you had the opportunity to design a lander, because at the end, I'm going to ask you to help me do that. Okay, so first I wanted to fly us around the solar system and look at some really cool dunes. Dunes are a form of wind blowing sand grains around and depositing these incredibly beautiful aerodynamic features. This is on Earth. This is in Namibia, so Southern Africa. The coast is right there, that little C shape. So we have this coastal desert, coastal dunes. Mars. So this is an active dune on top of lithified dunes. This is Venus. On Venus, we have, you can see these wind streaks. So the arrow there is pointing in the wind direction. This is Pluto. Our colleague, Matt Telfer, just found some methane ice linear dunes on Pluto, which I still think is a planet. And this is Titan. In the equatorial region of Titan, we have a whole bunch of linear dunes. And on Titan, what's crazy about the sand grains there is that it actually comes from the sky. So you have condensation nuclei in the clouds, and then all these small fragments start coming together to form, and then particles literally come out of the sky, which blows my mind every time Janie Rodenbaugh tells me that. We have Comet 67P, this big mystery that was going around a few years ago. We have some dune forms on there. So this is a function of some kind of fluid flow in a comet that doesn't really have an atmosphere, isn't supposed to. And we have these formations where sand has amalgamated in these very aerodynamic shapes. And the latest news is Io. So this is a moon of Jupiter. And like this was published a couple of weeks ago, Brian, I think, but it's the first time they found dunes on this planetary body. So this is a moon. It's got a low density atmosphere, and they believe, what our colleagues believe, is that windblown sand is forming these dunes as you have this differential between the lava flow and the frost on the surface, which is creating some vapor flows. And so you have pressure releases that induces a wind field, and then you're moving sediments around. Super cool. It's still blowing my mind. So we have all these dune formations that we see throughout our solar system. Can we use any information that we have from our windblown sand experiments on Earth to inform us about what's happening on other planetary bodies where it's really expensive and difficult to put instrumentation? So what I'm going to do is walk you through what our textbooks tell us, and then what our wind tunnel, very controlled environments tell us, and then what we see in the field, which kind of blows all that up, just to go ahead and spoil the surprise. And I'm going to show you some of the difficulties in measuring windblown sand, but also challenge you to think about how we can overcome those difficulties to adequately measure surface to atmosphere interactions on Mars and other planets. So the reason we want to do this is that winds throughout our solar system and beyond are redistributing surface particles across the surface. So sand is being blown around, but the mechanics of how it's being blown around are poorly understood. And even on Earth, we have a lot of issues, and I'm going to talk about that in a few minutes. But because we have these unconstrained mechanics, that prevents us from being able to really decipher the planetary rock record. For example, if Curiosity sees a stratigraphic column and you have some aeolian ripples, it would be really great to know when those ripples were deposited. And if we can say, oh, okay, well, this is what the grain size of that ripple is, then we can back calculate to say, well, this is the minimum wind speed, the threshold of motion required to move that grain or to drop that grain. So by taking those stratigraphic clues, that we can actually start recreating and helping us confine some of our estimates of the planetary evolution. It also, probably more importantly these days, it helps us predict dust emission. And Brian's been doing a lot of this with his dust devil work and his group here. And the reason we care about dust emission is the movement of sand grains on Mars, that's what emits a lot of dust. Same thing on Earth. It's much easier to move a sand grain than a really, really tiny particle where electrostatics are holding those particles together. Much easier to move sand. That's why we see dune forms on beaches. It's the easiest thing for water or air to move, sand-sized particles. So it's going to be the easiest thing on any other planet likely to move. So as particles are lifted, they hit the surface, they emit dust. Well, for human or robotic exploration on Mars, Titan, any of these places that we're going, this is a really important problem to have. If we're using solar panels, if they're dust covered, that's not very good. Also, as we're going to see with some of our instrumentation, dust is going to clog it all up. So we have an issue with longevity in our instrumentation. So how do we overcome this? Well, first, let's start with I'm going to say the easiest planet to study, only because we put a lot of money into studying it and it's pretty close to home, Mars. So most of this talk is going to be about Mars, but we have extrapolations that we can make about other planetary bodies. So the big paradox on Mars over the last 10 years, 15 years, is that we see a lot of transport. So this image that we're seeing here is a dune that is moving. Well, it's moving when our models say the threshold for motion, the minimum wind speed to move of sand grain is never reached. Well, that's a problem because we see sand grains being moved by the wind. We also see something like this. So this is from Curiosity observations. We have massive amounts of dust emission. Dust emission is a function of sand particles hitting the surface and emitting the dust. So, well, that's one of the major controls on dust emission. So the threshold is never exceeded. However, we see massive signatures where that's telling us different, where we think that sand is actually moving. So can we look at some of the observations on Earth to try to help us constrain this issue? So what Brian and his group have done here at Boise State have been looking at dust devils. So these are dust devils, which also emit dust into the air. So this is in Smith Valley, Nevada. And then these bottom images, this is Mars. So this is Opportunity. You can see one of the dust devils caught on camera here. And I just talked to Brian's team today, and they have found 300 to 500 dust devil events from, is it Perseverance data? Perseverance. That's so cool, because that means we're emitting a lot of dust into the atmosphere. And these are some orbital observations from MRO where you can see the shapes of these dust devils. So dust devils are also lifting a whole lot of dust into the atmosphere. And this is a video also from Brian's group. This is the process. So what I am completely obsessed with is the process. I see the form, we see it through imagery, we can see it at the Kelso Dunes, but what is the process that's driving and lifting these particles? So this is an example of dust lifting and dust emission through dust devils on Earth. And this is caught on Mars. So this is Curiosity catching some dust devils. So this process is what's emitting the dust into the atmosphere. By the way, once it's emitted into the atmosphere, it takes a really long time for it to actually settle out. This is a closer up view of a single dust devil. And I was really impressed by this video. So this is some of Brian's work as well. And I want you to note on that right side there, you see streamers. So that's the concentration of particles into organized structures. So we're going to think about that as turbulence throughout this talk. But it's a manifestation of a wind or a fluid shearing a surface and is organizing itself into these shapes. So I took a still shot from that video to kind of elaborate on this. So this is just some ways for you to visualize what these streamers are. So they're elongated concentrations of either particles like sand particles or dust particles. But what they do is they give us a visual hint of the process of the turbulence that's actually driving the transport. And that's really, really exciting. And so this is really similar to windblown sand that's just saltation. So this is just saltation. Saltation are sand grains that are bouncing along the surface in little hops, and they start moving together, and the turbulence actually organizes them into these streamers. So this is a video from my student Pete Taraskevich, who was looking at these, or caught these streamers a couple weeks ago. So, oh yes. Aeolian, oh, excuse me. Aeolian means wind derived. So Aeolus is the Greek god of wind. So that's where Aeolian comes from. So what is this process and how does it work? These bouncing of the grains, this emission of dust. This is what the textbook is going to tell us. The textbook is going to tell us that a single grain gets picked up, it hits the surface perfectly, it ejects other grains, and we know how to quantify that beautifully with no errors. That's not at all what we get, okay? So this is what we learn in school, and then after school, when someone asks you how to do it, you say, well, this is how you do it, and then they tell you, well, that's not what I see. So this is also one of the problems of my life. But this is physically what's happening. So we have saltating grains. You'll hear me talk about that. That's these bouncing grains that are coming in at a particular angle between 10 and 16 degrees. They rebound from the surface, and as they do, they eject particles, and those are called reptons. And so those reptons, if the wind is strong enough, they get accelerated, bounce a few times, and become saltons. And both reptons and saltons can also initiate creep, which are rolling particles. Who knew there was this much about windblown sand, right? Like, a lot of people actually spend a lot of time modeling this. So this is what the textbook teaches us. And this is what the wind tunnel teaches us. In a wind tunnel, we can actually control the wind speed. And that's great because that means we can isolate our variables and isolate the process. And it doesn't follow the textbook. Now, sometimes, like in this instance, we hit the surface and we ejected some grains. This is some of the work from my student Maddie Kelly at ASU. But then as that blue line you just followed, that particle didn't emit anything. So sometimes the model works and sometimes the model doesn't. This is the field version. Then you go outside and you say, okay, what does it really look like? This is from an experiment I did a few years ago now on a beach in North Carolina. And you can see the streamers, those structures are snake-like motions. They actually don't really follow a whole lot of what we were looking at, right? There's not this unidirectional, like, we have a grain and it hits perfectly, and then it's emitting other ones, and they're all operating on this line. Well, turbulence comes around and it organizes itself. So now we have a little bit of chaos that's thrown into the equation. This was last week doing some field work. This is my student Pete Taraskevich, and this is my PhD advisor getting pelted by sand grains. Sometimes that feels good to watch this video for that reason. I'm telling you, this was the craziest, sand transport I've ever measured. It was last week just outside of Palm Springs. Those are coarse grain streamers. On any beach that you normally go to, like on the East Coast, you have grains that are about 200 microns, 300 microns. These were 1,000. So this is 1 millimeter. And when they are hitting you, it stings. But it's really cool science. So we have coarse grain streamers, but also the height of the saltation, how high is actually bouncing, was 2 times what we typically believe. So in this instance, our textbook and our wind tunnel observations aren't really lining up with what we actually see. But doing this field work, and the reason we want to do this, and the reason we want to measure in situ observations on other planetary bodies, is so that helps us figure out where our models are wrong. That's me trying to take notes. That helps us figure out what's wrong with the models, and then we can attack that problem and then refine it. So it's an iterative process. So this is the textbook version of turbulence. So turbulence, as you are closer to the surface, you have some smaller fluctuations. And then as you move away from the surface, you have larger fluctuations from a mean. And that is representing, or that is a signature from eddies, different size eddies that are moving along a surface. You can imagine turbulence as like elongated tornadoes. So if you got a tornado and you stretched it, and then you had all these tornadoes interacting with each other. It's one very like cartoon example of how to think about it. And so the shape of this, the velocity profile of this is supposed to be logarithmic, and I think it is. And a lot of times it does follow the law of the wall, which I'll talk about in a few minutes. But sometimes it doesn't. This is an experiment I did in October, and I'm going to pause this for 1 second. So from the last image that I showed, right now, so we have those fluctuations that change from the surface all the way to away from the surface, right? So it's up into like the planetary boundary layer. We only have point observations. Curiosity and Perseverance, Viking, they only have a point. They have 1 point in all of this fluctuation. So how can we actually get reference or context to that? Well, on Earth, we use the law of the wall, and that's a Prandtl von Karman getting together and developing a set of equations to map out how the shape of the wind looks. Like, what is the shape of the wind? And we can use that if we only have 1 point measurement. But sometimes it doesn't work. So I was fortunate enough to get this proposal funded to develop the first filled particle tracking velocimetry system. And essentially what I do is I take little tiny helium bubbles and I let them go upwind of my measurement area. This is about 2.2 meters high. And there is a high powered laser that's being diffused and creating an elliptical volume. And so the laser is emitting at a wavelength that we can't see. We can only see it, and the reason things look green is because when it hits something, the wavelength that it refracts is visible. So as those helium bubbles move through this laser volume, the cameras in the back there, they actually record, and we can triangulate onto each individual helium bubble. And this is what I'm about to show you, which is what I'm really excited, is that this is the first time that we have ever been able to see natural boundary layer turbulence, not a point observation, but this is what turbulence actually looks like. Okay, hit it, play again. So sometimes we actually have structures, and sometimes see, there's a structure right there, and then sometimes it just bursts and erupts. So this is what wind actually looks like. I get so excited every time I see this, but this actually intimidates me, because how are we going to measure this? You know, like, I'm sampling at 800 frames per second. I don't know if we can do that on Mars. The traditional sensors are here over, you know, those sonic anemometers, which are measuring acoustically the 3-dimensional velocity fluctuations. And then we can have mean traditional sensors, which are giving us mean wind field measurements, so we can do the law of the wall. But turbulence doesn't, I don't know if capturing it at 1 point is actually going to be sufficient. And I'm a little intimidated after doing this experiment about being successful at actually measuring turbulence. I'm just going to play it one more time, because I want you to kind of notice the sampling volume of a sonic anemometer, which is the best we can do on Earth. This is the best we can do on Earth. And then what the turbulence actually looks like. So it's really a struggle to be able to say, hey, when someone comes to you and says, hey, let's design a lander, you're a field person, what do we need and how do we do it? I'm like, well, that's a great question. Let's all talk about it. But these are some lessons from the field on Earth that we can apply when thinking about these other planetary bodies. So I'm going to quickly go through this for time. But some of the research questions that I've specifically had are, between Earth and Mars, what's the threshold of motion? What's that minimum wind speed that if we saw a ripple in a stratigraphic record, then we can say this was the minimum wind speed at this point in time? That's incredible evidence for us. Also, how are the mechanics different, if they are different, between Mars and Earth? And can we predict how frequently the threshold is exceeded, because that tells us how frequently dust can be emitted and where it can be emitted. That's a really important question when we're sending humans or robotics to Mars. This is a classic diagram where grain size, the size of the particle, is on the x-axis, and the shear velocity, which is a height independent observation of the shearing stress. So that's just how much shear is imparting on the surface. That's what we actually use to predict the threshold of motion, but let's just talk about it as a minimum wind speed, unless you guys want to get into some real technical nerdy stuff. We can do that later. But what I want you to know is that red line, that's Mars. And this was Viking lander data, that finely dotted line, and the dashed line is Pathfinder and Phoenix data, that's wind data, deriving a shear velocity, and they're not exceeding the threshold of motion. Although we've seen from this presentation and from our colleagues' work that there's dust emitted all the time. We've got dust devils. We've got a lot of things happening that are emitting dust. So we've got a problem here with the threshold. These are some, well, you can't actually see it in this because of, if I minimize. Okay. So this is Viking. This is the wind sensors on Viking. So we have hot film anemometers. Hot film is just, it's putting out a temperature, and then as the wind blows it, that changes its temperature, and that can be correlated to how fast the wind is moving. That's how we have measured the wind speed on Viking, Curiosity, and Insight. And I believe on Perseverance as well. Brian and I are trying to get them to move beyond hot film anemometers because they're really good at breaking and not working. So we usually have limited observations. So this is Viking, and this is the measured wind speeds from Viking. So on that y-axis there, so this is a time series of when it started. So Sol 1, i.e. day 1, on to about day 1042. And then wind speed on the y-axis. Well, the threshold of motion is not exceeded. That's not good. And here's Curiosity. And then this is some wind data. Again, we have a time series, but this is like a little bit of a different time series. This is the time of day, and each of the colors represent a different period of time with wind speeds. The big point is that the threshold is never exceeded. So I designed some instruments and ran an experiment at NASA Ames, low pressure wind tunnel. We go down to the pressure that's on Mars. We use walnut shells for the density, or sorry, because we can't change our gravity. So we have to use that same gravitational ratio. And I can talk about that a little bit later. So we have walnut shells. And then we're recreating we're putting this into an atmospheric density of 0.02 kilograms per meter cubed. And so that is equivalent to what we typically see on Mars. So this is me slowly increasing the wind speed in the wind tunnel. And when the video first started, you saw a single grain move, then a couple grains, and then it was maybe like a good amount of grains, but then they stopped like that right there. And then as you continually increase, finally you get continuous transport. And whenever Dr. Ron Greeley was first defining the threshold of motion for Mars in this same wind tunnel, he looked at the point at which continuous motion was happening. And that's an important note for Mars work and the application to Mars. We're about to have like a Pink Floyd light show in a second of all the grains moving. Right, it's gonna get there. There we go. So this is all at low pressure. So it was a super fun experiment, but very stressful. So when Ron Greeley was trying to define the threshold of motion, or say what's the minimum wind speed at which we can move these grains, he looked to the only other person who had really done that, and that was Ralph Bagnall back in the 30s. And Bagnall did it because it was the only way to repeat an experiment back then, because that was the only way where it was like a constant way to visualize the motion. Well, on Mars, we need something before that. We need to understand the motion of single particles and the threshold for single particles. So on Earth, the fluid threshold was considered continuous. Ron Greeley a fantastic scientist who has taken us really far, did the same thing for Mars. But our thresholds, as we've seen, do not actually fit that. So I did some work, took those measurements, and I did a dimensional transformation where we take all of our parameters for Earth in our Earth experiment, and then we go through this dimensional transformation to say, okay, this is what I had in my experiment, and this is what that translates to on Mars. And what I found was really cool. The impact of a single grain on Mars, because it's so much less dense, as a saltating grain is bouncing around, the reduced density of the air means that it's not fighting as hard to get down to the surface. And so it's keeping a lot of its energy. So it actually hits the surface. So essentially the kinematics for a saltating grain moving over a surface are different. When you have a single burst of transport like that, or a single burst of particles, that leads to cascading transport. So the idea I talked about earlier, where we have a single grain, then ejects other grains, those ejected grains then, eject other grains, and so on. That's why our transport models are exponential functions. So this was a big deal. This is the paper that I got the awards for, which was really exciting. And I'm happy to go into more of that if you guys want. This was one of the figures from that paper. So this is grain size on the x-axis, shear velocity on the y-axis. And so all of our observations are the points, those yellow and purple points. So the cascading threshold, the initial for those single grains or patches of intermittent transport, that's what we're finding in those yellow dots. And then the purple ones, that's where we had the continuous transport. The dimensional transformation was taking that to a reduced level. So this is actually 1.6 to 2.5 times smaller than the original thresholds. And this is just showing, if we plot the grain size and the shear velocity, those two curves are our threshold model. And then that orange is where we have some observations. So this is our error bars. And we have maximum curiosity observations, the maximum wind speeds that actually fit it. So when we look at this and we compare that threshold to some of the wind data we have, Viking was exceeded a lot. Curiosity 5-minute averages were not exceeded, and we'll go into that in a second. Insight hourly average also didn't go in or get exceeded. And we know this is not true. We know that can't be right. And the reason it's not right is because we're averaging. When you average, you're filtering all those turbulent fluctuations that we saw in the green video on Earth. All of that's wiped out, and we just get an average. And so we actually aren't measuring with these single sensors the turbulence that can actually move sand grains. So it's those big fluctuations in turbulence that are initiating things. This is a PDF of Curiosity and Viking data. So this is just showing that we can, when we sample faster and we don't filter, we can actually see the threshold quite often. And it's really nice to know when we're exceeding the threshold. This is a diagram showing what time of day, with yellow being 7 in the morning, 7 to 10. And then as we increase in red, that's us going throughout the day. Well, we actually exceed the threshold of motion quite often, usually during the middle of the day, which is corresponding to what we're seeing on Mars. So we have new thresholds. They're within our observations if we're not removing or filtering out turbulence. The mechanics are fundamentally different. So we have higher kinematics for transport on Mars. Now, predicting the frequency of that is really difficult. There's a lot of assumptions that we make. There's a lot of assumptions in a lot of science that is done when it comes to in situ observations. But we're getting closer, and we know that that transport is happening much more frequently than we previously predicted. So if we're going to put sensors on Mars, which we have done and are going to continue doing, or if we're going to put sensors on Pluto or Titan or Io, what would we do? We have hot film anemometers that have been on our previous landers, but they're at a single height. What we need are solid observations of turbulence we need roughness elements, so how rough the surface is, and we need to be able to measure the sand transport. So there are 3 parameters that are going to get us really, really far as understanding planetary aeolian science. And so those are the 3 observations that my team and I are working on in conjunction with Brian to develop a lander to be able to measure all 3 of these different processes. So let's build a lander. That's it. And I legitimately want to build a lander with you guys. So like, I'm going to need some help. I'm going to turn the lights back on.
It's the top one. There you go. Perfect.
All right. Yeah. So on Earth, yes, and it's a combination of different instruments. So for turbulence, I've got the field PTV system, and my team at NRL and I are miniaturizing that so we can design it for Mars. So, you know, in that version that we have for Earth, it took like $2 million and a ton of people and big, heavy things that we can't send to Mars. It's not feasible. But on Mars, if we can miniaturize that, that'll give us unobtrusive observations of the turbulence there. And that's really important. So that's what we're leaning towards. As far as roughness goes, we can use high resolution LiDAR, so light detection and ranging, to be able to map out what the surface looks like. If you've noticed on any of the lander or rover imagery that gets sent back, it's not a perfectly flat surface, which like all of our models are built off of and want. So that's an issue. We have to fix that. So we can do that using a LiDAR, but also the application of that is, it gets a little difficult. Brian and I were on a call today where we were with some of these scientists that are on missions, where we're all debating, like, how do we measure this? And then once we measure the roughness, like, what are we going to do with that number? Which science question is it going to answer? And then the sand transport, I built a ton of different sand transport sensors for Earth. And some ideas from those are trying to be used for Mars. So one of like Don Banfield's piezoelectric strip. So he's using a piezoelectric strip to measure the saltating grains hitting it. So if something hits it, we get a little signal back that says saltating grains hit it, which is really cool. But we're planning on having that on one of the landers. But with the field PTV system, the miniaturized version that we're building, as sand particles move through that laser light and refract light back, visible light back, we can also track sand grains. So the PTV system that I'm building can do the sand transport as well as the turbulence, but we still need another sensor to be able to measure the roughness on the surface. Oh, okay, yeah, will do.
You guys have to after those videos. I have a question, Christie. You used walnut shells in the Mars wind tunnel.
Mm-hmm.
Who has to eat all the walnuts?
I don't know, but there's quite a lot. So the question was about walnut shells. So whenever we are running experiments in the Mars WIT, you know, we can change pressure. We can get the temperature kind of right, mostly not really, but closer. Essentially, we can recreate the density of the atmosphere that's on Mars. And that's awesome. That's really cool. But what we can't do is we can't change gravity. So the gravity on Mars is 3.7 meters per second, and on Earth, it's 9.81. So the reason gravity is important to sediment transport is that this sand particle is sitting on the surface and it has a weight because of gravity. So what we do is we use a particle shell that is, we use a grain size of a walnut shell, we use walnut shells that are sand grain size, and it has a density that is that same difference between 3.71 divided by 9.8. We use essentially a third of the weight of a typical particle that we see on Earth, which is mostly quartz. On Mars, it's basalt grains because there's a lot of volcanics that have happened there. So So walnut shells are about a third of the density of basalt particles when we do that conversion. So that's why we use walnut shells.
Because I assume he was. Do you know how he came up with walnut shells?
The question was, how did Ron Greeley come up with walnut shells? And I have no idea. I would wish he was here, but we could pick his brain. Yeah, John Marshall is still around from those original experiments. He's actually working with Lori at SETI, and now Don Banfield is there as well. So they have a whole team, and I bet John knows why. Yeah, and also when I was working in the Marswit, I didn't know that there was a company that actually had just buckets and buckets of walnut shells that I could buy. But apparently you can. If you ever need a lot of walnut shells, they're out there, ground up, and they're by grain size. Yeah.
Oh, so you showed us that asteroid at the very beginning of the presentation that looked like it had, I mean, it clearly has no atmosphere. It's probably very small, relatively speaking. And it had like wind-streaked dunes almost, probably not too big, but what are some ideas of how that worked?
Right. So the question was about Comet 67P, and we see these wind ripples on the comet, but we don't know how they formed. Right. If there's no atmosphere, then how can there be wind? I don't know the answer, to be quite honest. But yes, do you know the answer?
No, I don't.
Solar winds. I don't know.
It's too thick. So the comets have a very, very thin atmosphere. It probably is blowing very, very fast to make up for the fact that it's very low density.
So there is a thin atmosphere on the comets?
Yeah. They have a coma, right? So when they vaporize when they enter the sun, that produces some gas. Not enough gas, you wouldn't think.
Right.
I guess maybe somehow.
Right. Well, vapor flows are what they're thinking that Io is using to create those dunes. Yeah. Exactly. Vapor flows. The answer is maybe vapor flows. Yeah.
What is the minimum equipment you need on a lander if you were going on Mars or some other kind of lander to get an improvement in data that's
Okay. So the question was, what equipment do we need to put on a lander to make it worthwhile, or the minimum amount of equipment? This is a great question. And depending on who you ask, they're going to tell you different answers. And the reason they're going to tell you different answers is that numerical modelers are like, oh, these models work beautifully. We're just going to put one sensor at one height, and then we're going to use the law of the wall, and we're going to back out the shear velocity, and we know it's right. Well, if you do any field work, you know that is really hard to trust that number. In particular, on a planet where we have such strong temperature gradients throughout the day that we have a lot of convection. And so when we're measuring U, V, and W on Earth, it's not that W is not that strong, but on Mars, that W is really strong. So I'm not really sure that we can trust the law of the wall as much as we do. So that's a roundabout idea of saying, it depends on who you ask. If you ask me, I think you need at least 3 sonic anemometers so we can actually get the turbulence and how that's varying with height. I think we need a LiDAR sensor of some sort or photogrammetry with 2 cameras so that we can actually get what the surface roughness looks like, so that we can parameterize what the surface is doing to be able to shed those eddies, because the surface interaction with the wind is why we have that shape, that law of the wall shape. And then we need saltation sensors. We need a way to be able to measure the saltating grains, because essentially we're going to get a time series that says, okay, this is what my turbulence is and it's fluctuating. And then we'll have a time series of there's no transport, and then boom, we have transport. And so we can actually correlate those two, and we can say, okay, there is an in situ observation of the threshold of motion being exceeded. Or we can look at that variability in the shear velocity, and we can say, this is how many particles were moving at this shear velocity. That's going to help us refine our models tremendously. And if we have 3 anemometers, sonic anemometers, which the reason I want sonics is so that we can get 3-dimensional velocity fluctuations. If we have 3, then we can actually see how much that convection is really affecting our boundary layer. Yeah.
Question from online. Are there any wind ripples on the moon?
okay, question from online. Are there any wind ripples on the moon? I have no idea. So here's something also that's kind of annoying. If anyone finds out I study Mars, they're like, oh, you know everything about space, don't you? And so a lot of times I'm like, I have no idea. I don't know what that is. I've focused highly on wind blown sand, mostly on Earth and on Mars. No, I have no idea. I don't think so because there's no, well, you know what? I'm not even going to extrapolate some very vague, foggy ideas I have, but I have no idea. Does anyone here know? Ripples on the moon? Is there photo evidence of any?
There's no atmosphere on the moon. The moon has an exosphere, so it has a very, very thin layer of gas, but it's thin enough that it's basically kind of molecule atom at a time. It's not like winds that you're going to see even on a comet where you can actually get a fair amount of atmosphere. The moon doesn't have atmospheres. No evidence of any anyway.
Right, right. Except that like weird waving of the flag video that people are skeptical about. Yes. That's a great question. And I'm going to tell you what I think is going to happen, but I'm not completely certain. So the question was, because Mars is losing its atmosphere, how is that going to affect the emission of dust via dust devils? I think two things come to mind. One, if we have less of an atmosphere, then we have less wind, right? So that's one thing. But with dust devils, as I'm learning from Brian, you don't really want a whole lot of shearing wind. You want a lot of major temperature differences because that's going to cause a lot of local convection, which is going to initiate the dust devil. So I don't know, maybe if you started removing an atmosphere, started losing its atmosphere, you're going to get a greater temperature differential throughout a day. And so maybe there'd be a period of time where you'd have enhanced dust devil events. And then the atmosphere will go away and we would have questions like we do about Comet 67P. I mean, would you?
I think that's exactly right. Yeah.
Yeah.
Mars probably is especially from the atmosphere so thin.
Yeah.
Eventually, they'll be so long they can't do this either. I don't know where that limit is though.
I don't either. And so maybe that's what you're going to do for your dissertation. You'll find that limit for us. Yeah.
Are sand dunes on Mars or Earth larger and why?
So the question is, are the sand dunes on Mars larger or comparable on Earth and why? So on Earth, when we look at the Earth, we have these major pulses of sediment supply that have been deposited from some geologic time, a long time ago. And we have a wind in these big dunes. We've had a wind-filled or, Hadley cell kind of interaction that's kept this area drier and dustier and windier in this direction. So if you had unlimited sand supply, your dunes could grow until the boundary layer is actually you're affecting the boundary layer to where it can't form anymore. That's what happens in a lot of these places. So on Mars, I'm not really sure what the highest dune is, but they often take a little bit of a different shape. So if you look at some of the dunes on Mars, some of them have more gentle Stoss slopes. So the windward slopes of dunes, they're more gentle. On the Stoss slopes of those dunes, they have like mega ripples or ripples on them that are a different wavelength than we actually don't have on Earth. And there's some thought on that being because you have a higher kinematic viscosity on Mars, so that you are the saltation on Mars can act more similar to water moving sand grains around on Earth. So those are some of the differences, but I can't tell you which one and why you're going to have larger dunes. But it depends. If you have a lot of sediment supply, like you're getting pumped from whatever, then it's going to pile up. And if you have a wind direction that is supportive of building, yeah, so not sure. Yeah. So the question is, does my work for the Navy inform my work on Mars? So for the Navy, I do coastal science for naval operations. And the reason they care about windblown sand is that any ship to shore mission, if you're a Marine, for example, and you've got to go from a ship to the shore, think D-Day, for example, which is not a good day for the US. You have to know what that beach is going to look like for navigation and trafficability. Or let's say we needed to go rescue some folks in a particular area, and the location where you're trying to get them has mines where, if we're sending soldiers out, we want to be careful about that, right? So if you could say, hey, don't go until this time because those mines are going to get uncovered by the wind or they're going to get deposited, that's a really useful tactic for being able to actually do something successfully without hurting our warfighters. So that's why the Navy cares about windblown sand. And the scale I study is I study the small scale physics of how the sand moves things around, and I build instrumentation to better measure the process of windblown sand. And that has informed a lot of what we think about for Mars and how we take observations or how we predict the threshold of motion, some of the uncertainties that we need to figure out on a small scale. So because I study the small scale physics, we just replace like the density or the fluid or the particle, and it's going to act pretty similarly. So that's why I do the work, and that's how it informs what we're doing for Mars. And what it's also been really helpful for is that in the Mars community, so Brian and I are on this lander team, in the Mars community, a lot of the folks haven't been to the field, or they're numerical modelers, and they're super reliant on these models. Having my experience on the team has been helpful because I can talk about what has and has not worked, because I've done so much building of instrumentation, blowing up instrumentation, doing all kinds of things that that it's really helpful in like a practical sense of like how we actually measure it. Yeah. Yeah.
You mentioned saltation is one of the sort of fundamental processes.
Mhm.
Do we know, or can we make an educated guess as to whether that process works fundamentally the same, I guess, in a very thin atmosphere like on Mars, or a much denser atmosphere or medium, like, for example, Titan's atmosphere?
Titan, yeah. So the question is, do we know the behavior of saltation as it's on through these different planetary atmospheres that have different atmospheric densities? So what my Mars paper, the threshold paper, found is that because of the reduced density of the atmosphere, the particles are retaining a lot more of their energy when they're hitting the surface. So the molecules are much further apart, less dense. So when it hits the surface, it's moving faster. It's not getting as slowed down. And so that means the coefficient of restitution on the surface, if it's a hard surface, it's got a lot more energy still to keep going. So that feedback means that there's higher kinematics. There's a lot more energy that's being retained when you have a lower atmospheric density. For Earth, we have, well, let's go to Titan. Titan's easier, or maybe not easier. For Titan, we have a much more dense atmosphere, and there's actually a low pressure wind tunnel that our colleague Devin Burr in the late Nathan Bridges did a lot of work on, looking at the saltation transport on Titan. And it is suppressed. So you have a suppression of your boundary layer. So that fluctuation as we move away from the surface of wind speed. So that boundary layer is much, much lower. And those particles have to fight a lot harder to be able to get picked up and moved. But when they did those experiments, they were still seeing saltation. So the process can still happen, but it is modified. Mm-hmm.
Other questions? Why don't we give Dr. Swann another round of applause?
We didn't build a lander though. We haven't built a lander yet though.
And I'm afraid that we're planning out for tonight, so we won't be able to do any stargazing, but come back in June. Fingers crossed. I mean, June, it'll be clear, right? All right. Have a good night. Have a good
Thank you
weekend.
guys.